Hi everybody, Professor Jamer here. So today we're going to be learning about topic 18 and topic 19, which is all about friction. So we have three main types of friction here. The first one is static, which is when things don't move. And the example that's going to be given is that here we have an inclined plane with a given angle, and we have a box resting on it. And so we know the box has weight, which goes directly down. We have the normal force pointing straight up. And the static friction prevents it from accelerating downwards. The second case that we're going to be going over is kinetic friction. So in kinetic friction, we have something that's actively moving. So here we have a ground, we have a box, and we have it accelerating towards the right. And let's say that we have a force of tension pulling on it, and then we have this kinetic friction force that's opposing the motion, then we have the normal force, and then the weight here. The third case, which is something that we won't be getting to today, is rolling friction. So in rolling friction, we have something on an inclined plane or another surface, and it's actively rolling, and then we have this force due to friction that is opposing it, that's causing it to stay on the plane. So we have these three types of friction. So before we start talking about the equation of friction, let's talk about mu. So mu is the coefficient of friction, and it's a dimensionless experimental quantity, and we'll have a different coefficient of friction for each type of friction. So now we can think about it as it measures the interaction between objects. So if we have a shoe and ice, we're going to have a different and smaller coefficient of friction than if we have a shoe and gravel. So that makes sense because we have a more intense interaction whenever we're in between the gravel and the shoe versus the shoe and ice. It's a dimensionless quantity, and it's noted by mu sub s for static, mu sub k for kinetic, and mu sub r for rolling. So when we look at the coefficients of friction here, rolling is going to be the smallest coefficient of friction. Kinetic's going to be the in-between, and mu s is going to be the biggest. So if we had the same materials interacting with each other, mu r would be smaller, kinetic would be somewhere in between, and then static is going to be the greatest. And so it's an experimental property, and we use these coefficients of frictions, and we can measure them accordingly. So now let's talk about kinetic friction. So the equation for friction itself is going to be Fk, which is kinetic friction, is equal to mu k times n. So it spells fun. Friction is equal to the coefficient of friction times the normal force. So let's take the example that we drew up above. So here we have the tension. We have an angle that's about 12 degrees. We have a mass that's 3 kilograms. And we have an acceleration in only the x component of 1 meters per second squared. We'll also have the normal force and the weight. And then we have the kinetic friction acting against it. So in order to solve for the tension, we need to find the x and y components. So here we are given that mu k is equal to 0.3, which is the coefficient of friction, and we want to find the tension. So the x component is going to be, and the y component is going to be F net ma times the acceleration in that component. So we have t cosine theta minus Fk is equal to max for the x component. And in the y component, we still have Newton's second law, only that we don't have any acceleration in the y. And so now we have t sine theta minus mg plus the normal force is equal to 0. So you can see that we have two equations and two unknowns because we don't know the normal force, and we can solve for the force of friction directly using the normal force. So we have t cosine theta minus mu k times n is equal to max for the x. And for the y, we can solve for the normal force, where we have mg minus t sine theta is equal to the normal force. So now we can plug that expression of the normal force into the x component. So we have t cosine theta minus mu k times mg minus t sine theta, and that's going to be equal to max. So we can rewrite this as t cosine theta, and then we have two negatives, which becomes a positive. So plus mu kt sine theta minus mu k mg is equal to max. And now we can rearrange this equation of motion and factor out a t such that we can keep the unknown, one unknown, and then solve. So let's rewrite the equation using algebra. And now we can see that t is equal to mu k mg plus ma divided by cosine theta plus mu k sine theta. And so we know all these values. We know the mass is 3 kilograms, the mu k is 0.3, the gravitational constant is 9.8, and we can plug everything into this equation and solve for the total tension that we're pulling the box with. So we essentially plug the expression to the right into our calculator. And as we do that, we get the force of tension is equal to 11.82 divided by what's in the denominator, 1.04. So when you write that down, so then what you can see is that the force due to tension is equal to 11.37 newtons. And so that is how you solve this problem. So here we're not directly solving for the force due to friction, but we need to use the relationship of the force due to friction to find the tension. So now let's talk about static friction and the example that we wrote up above. So in static friction, what we have is, here's our inclined plane, here's theta, here's our little box. So we know the box has a weight mg, the normal force is pointing directly perpendicular to the plane, and then we have Fs that's preventing it from sliding down the plane. So we have to do the same thing. So we know that Fs is going to be less than or equal to mu s times n. So there's going to be a range of these static friction values that will prevent the motion of the box rolling down the plane. So let's pretend that we have a box and plane that are both made out of rubber. So we have a coefficient of static friction of 1. So the x component's going to be, and the y component's going to be split up together. So before we do that, let's redraw this using a tilted axis. And so we say that the x component is going to be Fs minus mg sine theta is equal to 0, since it's not accelerating anywhere. And then we have n minus mg cosine theta is equal to 0 for the y component. So if we say that the mass is 1 kilogram and the theta is 25 degrees, we can solve for the minimum static friction that is needed in this case. So here we see Fs is equal to mg sine theta, and we know that it has to at least be that amount in order to prevent the motion. We can have a much bigger static friction value and still prevent the motion. We know that n is equal to mg cosine theta, and let's plug in our values here. So we have n is equal to 1 times 9.8 times cosine of 25 degrees. And then when we plug everything in, we get a normal force of 8.84 newtons. And whenever we plug in our mg sine theta, we get a value of 4.14 newtons. So this is the minimum amount of force that we need in order to prevent the motion. So the maximum force that we need is Fs max, which is mu s times n, and here we see that we have a large normal force, and we have a coefficient of static friction of 1. So whenever we're looking at the maximum value of static friction here, it's going to be 8.8. So what we get is F of s is a range of values that we have on the interaction between the rubber and the inclined plane that will overall just prevent the motion. So we have a minimum value of 4.14 newtons and a maximum value of 8.88 newtons. So as long as we have a static friction force somewhere in between that, we're actually effectively preventing that motion. So static friction is a little less intuitive since we're just preventing the motion, and it could be a range of values. And so we can say that Fs max is equal to mu s times n, and so that's the absolute maximum static friction force that we have in this problem. It's still mu s times n. And so our range of value is going to be 8.8 newtons is going to be the maximum, and the minimum is 4.14 newtons. And so we use the method up above in order to find the minimum force needed because we had all our values right here. And we also used our normal force in order to solve for the maximum value that we have. So essentially we have this range. And so we know when we're at the maximum case, and we know to set it equal to when we have phrases like we're on the brink of motion. Meanwhile, if we want the minimum, we just use the method above. So if we're using the phrases on the brink or just about to move, then we're using the Fs max. So that's what we mean by Fs is less than or equal to mu s times n. So whenever we're using on the brink or about to move, we use this maximum case. So thank you so much for paying attention today. This is how we can effectively solve for the static and kinetic friction of these problems and types of problems, and we just kind of showed how to set them up today. So thank you so much, and let me know if you have any questions. Bye for now.